As we go from 6 to 5 to 4 to 3, remember the rings. As the rings compress, the energy of the cyclic species, the energy of the ring, essentially rises. And as we see here, the difference between the cyclic and the acyclic version, that difference expands. So I have two questions to ask and answer. Question 1. Why is the ring, in general, less stable than the acyclic species? What is wrong with the ring that the energy of the ring is, except for cyclohexane, that the energy of the ring is larger than the energy of the acyclic counterpart? That's question 1. What's wrong with being a ring? That's question 1. Question 2 is, why does the ring why as the ring compresses from 6 to 5 to 4 to 3, why does the system get increasingly more energetic, increasingly less stable? Right? So those are the questions we're going to ask and answer. And then as a corollary to that second question, what is magical about C6? Why is C6 in the sweet spot where the acyclic and the cyclic species are exactly the same? So question 1, what is wrong with being a ring? Right? Why is my ring more energetic than my acyclic species? And the answer is that it has to do with what's called ring strain. It has to do with what we call ring strain. And strain suggests high energy, right? So straining to lift something is a high energy state. Ring strain is the strain, the discomfort associated with being cyclic. And it turns out that ring strain has two origins. One is angular strain, and the other is torsional strain. So ring strain is the strain, the high energy state of simply being cyclic. And we know that exists because we're seeing it here. Okay? The question is, why does it happen? And it happens because what makes a ring unstable, what adds to the strain, is a combination of what's called angular strain and torsional strain. Okay, what is angular strain? Angular strain arises from distortion of a carbon-carbon-carbon bond angle away from the 109.5. So the classic bond angle for an sp3 hybridized carbon, and all of these are sp3 hybridized, the classic bond angle for an sp3 hybridized carbon is 109.5. Well, if I look at these, that's 109.5 in the cyclohexane, so that's not a problem. But here, that angle is 108 degrees. As I've written this as a square, which as we see in a second is not quite, as I've written this as a square, that angle should be 90 degrees. As I've written this as a triangle, this angle should be 60 degrees. So these angles are going from the 6 to the 5 to the 4 to the 3, we're moving further and further and further away from the classic value. Now, it is the classic value in cyclohexane. So cyclohexane has no angular strain. Has no angular strain. Cyclopentane has a little. Cyclobutane has a large amount. I mean, that's almost a 20-degree difference. And it's a massive amount in cyclopropane. And obviously, what this means is that if you are sp3 hybridized, your angle that gives you your native angle, your angle with your comfort is 109.5. That's when your bonds are furthest apart in three-dimensional space. Right? That's why I want to be 109.5. That's the classic value predicted by the VSEPR because it leads to greater stability. Least strain. But as I constrain the ring from 6 to 5 to 4 to 3, my bond angles decrease, and I am moving I'm bending further and further away from my comfort zone, I become uncomfortable, my energy level goes up. We'll see in a second, this actually turns out not to be a right angle. This is actually 88 degrees. In other words, the strain is, the angle strain is even greater. So that's the angle strain. So there's no angle strain in cyclohexane. A little in cyclopentane, and it gets larger as the ring gets smaller. What is torsional strain? Well, torsional strain is the strain associated with twisting, with rotation. And we talked about rotation, about conformational analysis last day, and we talked about twisting or rotating about a carbon-carbon single bond. So, torsional strain, I think you guys can see from here, torsional strain is a strain associated with twisting, but more specifically, with being eclipsed. So if I look at butane, this represents my highest energy state, right? Where my two methyl groups are at a dihedral angle of 0 degrees, okay, of 0 degrees. So this represents a high energy state. And torsion refers to twisting, and torsional strain refers to the strain of being eclipsed, right? When my large groups, when my groups are, right next to each other, dihedral angles of 0 degrees, particularly when I'm dealing with a large group, okay? So, what we're going to do is see how those two types of strain play out in the various rings. How they play out in the various rings. So I guess you guys can see here. Let me just make sure this is in view so you guys can see. Yeah, that'll work. Okay. So let's build propane and cyclopropane. And if you guys do not have a set of models, and particularly if you're going to be taking Organic 2, I would recommend that you get yourselves a set of models. They're very useful. Okay. So here is propane. And I have free rotation about the carbon-carbon bonds in propane. So propane is free to adopt a conformer in which all of the H's are eclipsed, right? Or not. It can rotate out of that quite easily into a conformer, which would be the most abundant one, where all the H's are staggered. So this would be the most abundant conformer in propane. And I have free rotation where I can rotate out of an uncountable conformer. Let's make cyclopropane. Now this is going to get kind of weird because the model doesn't like to be bent like that. Okay, so you have to imagine these lines are straight. Well, first of all, if I look at propane, my bond angles are all 109.5 degrees. So I have no angle strain in propane. I have no torsional strain really because I can rotate out of being eclipsed. So I lack angle strain, I lack torsional strain. Propane is in good shape. If I look at cyclopropane, my bond angles are 60 degrees. That is a massive departure. That is a 49.5 degree departure from the value of 109.5. That is, which is the optimal value for an sp3 hybridized carbon. Any distortion above or below that value creates strain. So cyclopropane has got a lot of strain. In fact, it's got the most angle strain. But if I look at cyclopropane also, beyond angle strain, all of my H's in cyclopropane are eclipsed. Right? This is eclipsed with that, it's also eclipsed with that. This is eclipsed with this and that. If I turn the ring over, these are eclipsed with each other. So every single H in cyclopropane is eclipsed. So there is massive torsional strain. But unlike propane, which can rotate out of being eclipsed, Cyclopropane can't. The ring has absolutely no flexibility, so we are stuck. So cyclopropane has a massive amount of angle strain and a massive amount of torsional strain because I can't twist out of it. All of my H's are eclipsed, they are permanently eclipsed, that's bad. So it's not surprising then that the cyclopropane-propane gap is the largest. Because cyclopropane has the most angle strain and it's got a lot of torsional strain. This is bad. Okay, let's make instead cyclobutane. And as you can imagine, if I were to just have butane proper, so if I just have butane proper, right? Butane, like propane, and we'll take this as a given moving forward. Butane, being acyclic, does not have any angle strain. All the bonds are 1 and 9.5. Alright? It's acyclic. Butane also need not have any torsional strain because I can rotate into conformers in which all of my groups are staggered. Right? Staggered here, staggered here, staggered there. I have the option of rotating out of an uncomfortable situation where everybody is eclipsed. Right? And I do that 1,000,000 times per second. No, actually, 1,000,000,000,000 times per second. If I look at cyclobutane, however, if cyclobutane existed in this arrangement, my bond angle would be 90 degrees. That's bad. Plus, I'd also have every single H in cyclobutane eclipsed. And that's bad. That'll be just as bad as cyclopropane. But if you look, cyclobutane has a little bit of twistiness. There is some residual freedom of rotation in cyclobutane. It's not a lot, but it's enough to twist the groups so that we're not entirely, so that one set is not entirely eclipsed. Now if I twist it, you can see this one, this set is, okay, so that set is eclipsed, but I can have these two, it's not staggered, but it's not quite eclipsed. And it'll take turns rotating, the flexibility takes turn rotating around the ring. So at some point, this one is slightly, it's not quite staggered, but it's slightly staggered, and then this one will be, and then that one will be, and so on. So I can decrease, to some extent, my torsional strain. The trade-off is that I decrease the bond angle even further. So the bond angle, if cyclobutane were flat, the bond angle would be 90 degrees. But I would have massive torsional strain. In an effort to release some of the torsional strain, I would take advantage of the flippiness in the ring, some rotation, bend it, so that one group is not quite staggered, but it's close. But what that does is it makes the bond angle in the ring lower. So I sacrifice, I take more angle strain in order to relieve torsional strain. And that says a lot about your priorities. Okay? So cyclobutane then is more stable than cyclopropane for two reasons. One, the angle strain is lower. It's only at 88 degrees, and that is a good 12 degree less worth of angle strain. Okay? But also, the torsional strain is not quite as severe because I can take advantage of the increased flexibility in the ring to twist one methylene group at a time, trillions of times per second, so that on average there's at least one group that is not fully eclipsed with its neighbors. As you can imagine, if I were to make cyclopentane, the situation I would expect would be even better, because we saw that when we went from a 3 to a 4, the ring got more flexible. Well, you can imagine if it gets to 5, it's a lot more flexible still. Now, if cyclopentane were flat, my bond angle would be 108, okay? And all of my H's would be eclipsed. If it were flat, all of my H's would be eclipsed. Well, that's bad. So what I want to do, as we did with cyclobutane, is to take advantage of the flexibility, which is now significant here, as you can see. Take advantage of the flexibility and pucker it. And now when I pucker it, if you notice what's happened, this methylene is now entirely staggered with the two next to it. It's entirely staggered with the two next to it. When I had cyclobutane, I couldn't stagger it. I got it slightly away from being eclipsed, but it wasn't quite staggered. So this is a lot better. Now, if I stagger this one, you notice that the ones here are still eclipsed. But I can take advantage of the rotation, and this one will enjoy the sweet spot for a femtosecond, and then this one would take its place. And then this one would take its place, and so on. So that puckering makes its way around the ring trillions of times per second, so everybody gets a chance to get a breather. And this is a good breather, because for that instant, I am staggered. So in cyclopentane, right, I have a bond angle of 108, so there's little angle strain. I do have less torsional strain because I can get one methylene entirely staggered. Okay? And that makes its way around the ring, so there's some angle strain and some torsional strain. But it's a lot better than the cyclobutane or the, God forbid, the cyclopropane. Okay? Now, when I make cyclohexane, and you can obviously tell where this is going to some extent, when I make cyclohexane, first of all, if cyclohexane were flat, that would be bad because everybody would be, everybody would be eclipsed. Okay? And that's bad. My angle would be 109.5, so there's no angle strain. Right? There's no angle strain in any version of cyclohexane. But if it were flat, then I'd have torsional strain. But as you can tell, there's a lot more flexibility in cyclohexane than there was in cyclopentane, even cyclopentane. Oh, shoot. I should go back to cyclopentane for a second. I'm going to make cyclopentane again. There is a term we use for this conformer of cyclopentane. This is called the envelope conformer, because you have to use your imagination here a bit. It's taking an envelope and opening it. So this is the flap. This is where you lick. Well, you don't lick anymore. You get one of those little wet pads and do this, and then you fold it over and you seal the envelope. Right? So this is called the envelope conformer of cyclopentane. So if I go back to my cyclohexane, right? So as you can imagine, cyclohexane is not flat. It'll take advantage of the flexibility in the ring, and it will rotate into conformers that will attempt to minimize the discomfort. So first of all, we recognize that there are two very distinct types of conformers in cyclohexane. I'm going to preface that by saying that is a simplistic way of looking at it. If this were a graduate class, we would talk about several different subspecies that are present. But for intraorganic chemistry, we're going to define two extreme conformers of cyclohexane, neither of which have angle strain. There is no angle strain in cyclohexane. This conformer is called the boat conformer. Takes a little imagination. So here is the bow, the sprit. This is the deck of the boat, right? And the boat is sailing along the river or the ocean. This is a boat conformer. Okay? So I'm going to go ahead and draw the boat conformer of cyclohexane. And it looks something like this. So the boat conformer, I can draw it to look something like this. So I have H's on the deck. And then I have H's here. This interaction is called a bowsprit interaction. But you also have these interactions, which are torsional, because these groups are eclipsed with each other. Okay, so I'm going to bring this close to you so you can see it. Yes. So my bowsprit interaction is this interaction. See, you can always hear them clicking, right? That's bad, right? Because I've got my groups now rubbing against each other. That's pretty bad. So this is a bad interaction. But also, the H's on the decks are eclipsed with each other. These are eclipsed. These are eclipsed. These are eclipsed. These are eclipsed. Right? I would not consider this eclipse. I should not have drawn that. Because they're not an adjacent carbons. Let's see, so bowsprit. Yeah, okay, no, I guess that's fine. Yeah. Okay, so yeah, so the boat, even though it has no angle stream, has a significant amount of torsional stream arising from the eclipsing of the H's on the deck, as well as a new kind of torsional stream, which is the bowsprit interaction. So the boat is actually not particularly stable. Not to worry, we will take advantage of the same of the increased flexibility by rotating out of the boat conformer. So the way I do this is I'm going to hold one of these methylenes. Oh, by the way, even in the boat, the H's, the methylenes that are puckered, are staggered with the methylenes on the deck. Right? The methylenes that are puckered are staggered with the methylenes on the deck. Okay? But it's not great because I've got torsional strain because of the eclipsing. So here's what I'm going to do. I'm going to hold one of the methylenes, let's say carbon 1, so 1, 2, 3, 4. I'm going to hold one of the methylene stationary at carbon 1. I'm going to take the methylene at carbon 4, and I'm going to rotate it all the way down. Okay? I'm going to do it again. Here is my boat, bowsprit. I'm going to grab carbon 1, take carbon 4, and rotate it all the way down. Now when I look at this, two things are true. There is no angle strain. There is never angle strain in a cyclohexane. But now, if I look at it, nobody is eclipsed. Every single methylene is staggered, which means there is no torsional strain. For heaven's sake, if I have no angle strain and I have no torsional strain, I have no ring strain. If I have no ring strain, then I should be almost equivalent to my acyclic, oh I took it off. I should be equivalent to my acyclic counterpart, hexane, which has no angle strain or torsional strain. Which is why cyclohexane and hexane have roughly the same delta, the delta H of combustion was functionally zero. Because cyclohexane has no angle strain or any torsional strain, no ring strain. Now, there's a chair, this is called a chair conformer, we'll get that in a second. Now there's the boat. But if I'm a molecule and I have a conformer which is a lot more stable, then in a sample of cyclohexane, 99.99999% of them will exist in this conformer, which is a more stable one. And you only have 0.00001 or something of that nature existing in the boat conformer. So to all extents and purposes, we can ignore the boat. right? The boat might exist for a femtosecond, but it might be only one of a trillion molecules in the boat conformation at any given time. The abundance of cyclohexane molecules will be in this conformer. What do we call this one? We call this one a chair conformer. And this takes a bit more imagination. The chair is an extended lazy boy. So you can imagine that this is the back that you're leaning back on. This is where your butt would go. And then your legs would fold over this part. This would be the pocket for your remote control. That's the pocket for your soda or whatever you drink, or your coffee or whatever, or your beer, I guess. So it's an extended lazy boy. Back, butt, the back of your legs folding over here. Okay? It's an extended lazy boy. So it's called a chair conformer. We want to get some practice drawing the chair. And what I want to point out is the chair really is a beautiful pattern of symmetry. And it's a pattern of symmetrical lines. Okay. Let's look at the bonds that make up the ring. The so-called endocyclic bonds. Remember that term from before? Endocyclic, meaning within the ring. So we're going to look at the endocyclic bonds, right, which are the bonds that make up the ring. And, yeah, I was writing it down. So you have endocyclic, which are the ones that make up the ring, and then you have exocyclic, which are the ones coming off of the ring. Right? So my bonds in a ring fall into two categories, endocyclic and exocyclic. So I want you to see this before I go and draw it on the board. It is a series of parallel lines. This endocyclic bond is parallel to this one. This to that one, this to that one. Okay? Sets of parallel lines. That's the endocyclic bonds. If I look at the exocyclic bonds, really they're of two types. There is one set that points vertically up and down, vertically up or down. So up, down, up, down, up, down, and they alternate. If I were to kind of squint my eye and imagine that the cyclohexane was kind of flat, which is not, but I'm going to say roughly kind of flat, these bonds that are vertical would be along the axis of the molecule. Right? I could rotate about the axis. So I'm going to call those bonds that are vertical, up or down, I'm going to call them axial bonds. And if I kind of squint and imagine this being flat, then the other ones, which are up and down at angles, right? Up at an angle, down at an angle, up at an angle, and so on, I'm going to call those bonds equatorial bonds. Now, what are the contours leading to the axial bonds? Let's see what I mean by that. If I look at the endocyclic bonds leading to this one, they're both going up. And so the axial goes up. Now, the bond angle, whether it's carbon-carbon-carbon or H carbon-H, must be 109.5. So if my axial points up, my equatorial must point down. The endocyclic bonds leading to this carbon are both pointing down. So the axial points down. The endocyclic bonds leading to this one are going up, so the axial goes up. And really, once I fix one, I know the others, because it's up, down, they alternate. And then the equatorial bonds also point in the opposite direction. So the axial points up, equatorial points down, but down at an angle, not straight down. Okay, there's something else. The equatorial bond is parallel to the endocyclic bond 2 positions away. The equatorial bond is parallel to the endocyclic bond 2 positions away. So this equatorial is parallel to that equatorial. This equatorial is parallel to the endocyclic bond 2 positions away. 1, 2, so these are parallel, or 1, 2. So these are parallel. Because we already said this one and that one are parallel. So I'm going to use this information, my understanding of the geometry of the ring, to draw the chair. So I'm going to draw a series of parallel lines. So this one, that one, that one. Okay? So these 2 are parallel, these 2 are parallel. These 2 are parallelish. Right? That's close enough. Okay, so parallel, parallel, parallel. Let me draw the exocyclic bonds. Well, I'm going to start with the axial. They're a little bit easier. Axials go up and down vertically. Where will the axial for this one be? Well, the endocyclic bonds are going up, so the axial goes up. And really, once I've done that, I know the others will be down, up, down, up, down. But I can verify. The endocyclic bonds leading to this carbon are going down, therefore the axial is down. These are going up, so the axial is up. These are going down, so the axial is down, and so on and so on and so on. Where are my equatorials? Well, the equatorials point away from the axial, right? If the axial is pointed up, the equatorials will point down. If the axial is pointed down, the equatorials will point up. But I also know that they point always away from the body of the ring. In other words, there is nothing on the inside. Because if I put them on the inside, the H's will be butting against each other, that's not good. So the equatorials always point away from the body of the ring. Up and down, at an angle, not straight up and down. In opposite direction from the axials. Parallel to the endocyclic bonds 2 positions away. And always away from the body of the ring. So, where are my equatorials? Well, if this is pointing up, if my axial is up, and again, so this is the axial, which is abbreviated AX. If my axial is pointing up, my equatorial points down at an angle. And the angle has to be 109.5. I don't want you to measure it, but I want you to draw it so that it is 1, pointing away from the body of the ring, and 2, parallel